Yo, welcome back. All right, so now we're going to continue with estimating derivatives in some other ways. So, how to estimate a derivative, and we'll start with the table. So, here's a table where you have some x values, you have some corresponding functional values, and you have some corresponding derivative values, right? So, for example, this 4 means that the derivative at 2, so if you did g prime of 2, it would be 4. So, the slope of the tangent line on the graph of g at x equals 2 would be up 4 over 1. So, that's kind of how that's the info that that table's given us. So now it says estimate g prime of 5. So how do you use tables to estimate derivatives? Well, if you remember, we started this whole conversation off with average rate of change and instantaneous rate of change, right? We used slopes of secant lines to approximate slopes of tangent lines, right? And so that's the same deal here. So if I want to approximate the derivative, I'm going to find out, well, first off, where does 5 lie, right? So 5 would be somewhere between 4 and 6. So this is what I'm looking at right here, right? So it's almost like, again, this isn't not even close to drawing a scale. It doesn't have to be. I'm just going to try and give you a visual. So at x equals 4, you have some functional value 5. And at x equals 6, you have some functional value 2. And the function, right, is differentiable. So we're going to learn more about that. But it basically means it's also going to be continuous. And now I want to estimate the slope of the tangent line at 5. So if I was to come over and draw in, oh, my orange didn't take. All right, come over and draw in a tangent line, right? I want to estimate that. So how am I going to do it? Well, I'm going to do it by go ahead and figuring out the slope of the secant line that kind of like encompasses that tangent line. So we're going to use the secant to approximate the tangent. So this, in particular, the slope of the secant to approximate the slope of the tangent line. All right, so let's go get them. So how do I find the slope of the secant line from 4 to 6? Well, all right, it's FB minus FA over B minus A. Or in this case, right, it's going to be G of B, or in particular, G of 6 minus G of 4 all over 6 minus 4, right? That's basically change in Y values over change in X values. So what the heck is G of 6? G of 6 is 2. All right, so this is where it gets a little dicey. I'll do g prime of 5 approximately equal to, so that's 2 minus, all right, what's g of 4? Well, that's going to be 5. 6 minus 4 is 2, so I end up getting that g prime of 5 is approximately equal to negative 3 over 2. So the slope of this tangent line is approximately equal to down 3 over 2. And we did it by using the slope of the secant line. It's kind of like what the calculator did in the last video, just for a much smaller interval. All right, where this is a lot rougher, and you can only use what you have, which is this is the values in the table, right? So since we wanted g prime of 5, that's why we use this interval. If they wanted you to estimate g prime of 3, well then guess what? You would have, that 3 is here, you would have did that interval. Guess what you didn't need at all? You don't even need to know the derivative values, right? This doesn't help you, right? To approximate the derivative on this interval, you're going to do what we just did here. All right, so this is kind of like a distractor for this question. All right, let's keep going with this. All right, so, whoa, I don't know how that happened, but we will go back to it. All right, so let's take a look at this one. Very similar. So the table below gives the values of the differentiable function f and its derivative f prime at the selected values of x. Use the values of f from the table. Estimate f prime of 4. So like, okay, where would 4 lie in these x intervals here? Well, 4 would lie somewhere right there. So then this is what I'm going to do. I'm going to find the slope of the secant line that's passing through these 2 points. So I would literally write f prime of 4, and I don't write equals. I write approximately equals. I cannot tell you how huge this is for you to do that. It's huge. So I'll write it down. Huge. Right? Don't write equals. So now the slope of the secant line, f of b minus f of a over b minus a. So in this case, it would be f of 5, that's the b, that's the right endpoint, minus f of the left endpoint, f of 3, all over 5 minus 3. So then I'll come down and carry this along. F prime of 4 approximately equal to f of 5 is 4, f of 3 is negative 1. Got to be careful there. 5 minus 3 is 2. So now I get f prime of 4 is approximately equal to, this would be 5 over 2. So the slope of the tangent line on the graph of f at x equals 4 is going to be about 5 over 2. And again, I'm using the slope of the secant line to approximate the slope of the tangent line. Again, this column, not needed at all. All right, let's go now to the next question. Here's a typical AP question. They try and confuse you by writing a paragraph. All right, so let's just sift through all the nonsense and you'll see this is exactly like the first two questions. So it says, as a bowl of soup cools, the temperature of the soup is given by a twice differentiable function. All that means is it's a function that you can take the derivative of twice. All right, and it happens to be defined on the interval from 0 to 12. And that's what we have in the table here. It says where h of t is measured in degrees Celsius, which is nice because they told me that right here. If they didn't, I would come over here and be like, hey, that's measured in degrees Celsius. And time is measured in minutes. Same deal. They told me in the table, but if it didn't say that, I might put that down. It says values of h of t at selected values of time t are shown in the table below. Use the data in the table to approximate, here we go, h prime of 5. So to approximate the derivative at 5, so where would 5 lie? 5 is going to lie somewhere in here. So here is what we're looking at, right? So I would say h prime of 5 is approximately equal to, right? The slope of the tangent line of 5, we're going to approximate it by using the slope of the secant line, f of b minus f of a over b minus a, or in this case, h of b, h of 8, h of that right endpoint, right? Y value at the right endpoint minus y value at the left endpoint over subtract the two x values, 8 minus 3. And so h prime of 5 is approximately equal to h of 8 is 67, h of 3 is 80, and then 8 minus 3 is 5. So when I do the numbers here, I'm going to get, let's see, that's what, negative 13 over 5. So not that I have to convert it to a decimal, there's no need to it, but what is that, negative 2 3/5, 0.6, right? So what does that mean? That means the slope of the tangent line in the graph of h at 5 is negative 2.6, down 2.6 over 1. Now, what does it mean in the context of this problem? Well, you can always get context of problems by looking at the units of whatever it is you're studying, right? Think about how we got this negative 2.6. We got it from this difference quotient. The numerator in this difference quotient, right, are h values. What are they measured in? Degrees Celsius. The denominator, right, are t values. What is that measured in? Minutes. So what do you think the unit for my derivative is here? It's going to be degrees Celsius per minute. Right? And that's how you can always get the unit for a derivative. Just take the y unit, divide it by the x unit, and that'll give you meaning. So that means, if you think about it, at the 5th minute, at t equals 5, at the instant t equals 5, right? The temperature of my soup is decreasing, because it's negative, 2.6 degrees Celsius per minute. It's almost like the speed of the soup temperature, okay? So at t, and this is how you explain it. At the instant, you always got to mention that at that point. At the instant, t equals 5 minutes, the soup is decreasing by 2.6 degrees Celsius per minute. All right? So that's some good stuff right there. All right, let's go on. So let's switch gears. And now, how do you estimate derivatives from graphs? Well, you should kind of know this, but let's just do it. So it says the graph of the function f is shown below. So we got a little piecewise type function, piecewise defined function. Is the graph of f has a horizontal tangent. Again, that's not an asymptote almost. That's a horizontal tangent at x equals 5. And all that means is 4, I should say. All that means is if I went over to 4 and I drew in a tangent line, it would be horizontal. So in other words, the slope right here, m, would be 0 at that spot. All right, maybe we'll need that. Maybe we won't. We'll see about it. All right, then it says, and it's concave down from 0 to 6. So what does that mean? That means the graph is curved down. So this portion of the graph we would consider to be concave down, as downward curvature, right? From 6 on, the graph is linear. Well, that makes sense because that looks like a line. We can see the jump here. And now all that nonsense, it says go ahead and approximate f prime of 5.5. So hopefully we know what this means. This is the slope of the tangent line at x equals 5.5. So I would go over to 5.5. That's somewhere like right there. I would go up, make a dot here, and do my best to draw in a tangent line. Right? It'd be better if I had a ruler. And so, all right, I had to approximate that slope. Well, I mean, I fudged it a little bit, but you can see it looks like I'm going through that grid mark and that grid mark. So it looks like if I can find two grid marks that I go through, it's just random that happens at the edge here, wherever I can find two grid marks that I can go through, it looks like it's going to be down 1 over 2. And again, that's an approximation. It might be a little off. So I would say that f prime of 5.5 is approximately equal to down 1 over 2, or negative a half. And literally you get that by just drawing in a tangent line. Now, if your tangent line does something like that, and you're like, well, it's not really going through points, then keep sketching it, keep elongating it till you get it so that it actually goes through a grid point and goes through another grid point somewhere over there, so you can figure out the downs and ups, or the ups and overs, I should say, rise over the run. Okay? All right, so not too bad. Luckily, I didn't ask you what the derivative was at 6, because that would have ruined your whole day, because you couldn't have found that. But again, more to come on that. All right, so let's take a look at this guy. It says graph f prime of x. So now I'm asking you to graph the derivative. And you're like, what? How are we going so bananas? First, it's just evaluated at certain points, and now you want me to graph a derivative? Well, first off, it should make sense that you can graph a derivative, right? I mean, think about it. Before, in a video prior, we did f of x was ln of x, right? And we found that its derivative was 1 over x. So I can graph both of these functions, right? Because the derivative is also a function. All right, so that's not what's going on here. They didn't give you the function, but maybe we can still graph it. So it says, all right, here's absolute value of x, and I want to graph f prime of x. And the way I set you up here is I put some points in. And like, let's figure out what would the slope of that tangent line right there be? Right? Notice I didn't extend it very far, but the slope of this tangent line is the same as the slope of this line. And if this is really absolute value of x, right, we've seen this enough this year, that means it's x when x is positive, and it's negative x, that's this branch here, when x is negative. And it's 0 when x is 0, but I can also do that. So, all right, that means this is the graph of x, this little branch here. So whether I draw the slope of the tangent line in there, or if I draw it in there, or if I draw it in there, all of these slopes, hopefully you're thinking, are up 1 over 1, right? So they're all up 1 over 1. So now think about this. I have a correspondence. When the x value is 1, the slope of the tangent is 1. All right, so when the x value is 1, the output is 1. When the x value is 2, the slope of the tangent is 1, right? When the x value, I didn't do it, but what if I did it at 1.1 or 1.2 or 1.3? The slope of the tangent, right, no matter what x value I use, the output for the derivative is always going to be 1 as long as I'm greater than 0, right? So that is a partial graph of the derivative, right? But now what happens over here? Well, if I draw in these tangent lines, and I only picked 3 random points here, but I think you would agree that if I picked any x value that was less than 0, no matter where I go and look at it, the slope of the tangent line at that x value will always be the slope of that line, which is going to be negative 1. All right, so I would end up getting that. So this actually, believe it or not, is going to be the graph of my derivative. Notice I label my y, my x, and the actual function. Now, what should be driving you a little bit nuts is, well, what about at 0, right? So notice I left that out. And it turns out that the derivative would not be defined there. And when we talk about differentiability, we'll get more into that. But whenever you don't have a smooth transition, like here, it's kind of like a rigid transition or a corner. Like if you're on a roller coaster, this would be like a bad roller coaster, right? That means that you can't find the derivative there. The other thing you can think of is like, well, how would you draw the tangent line, right? So I can kind of like almost weeble wobble. Like I could draw that, I could draw that, I could draw that. I could draw a whole bunch of lines here that would be like weeble wobbling at that point, and that's no bueno. All right, but there's going to be a lot more on that. Long story short, you can't find the derivative at a corner. It doesn't exist, right? It's not defined. And you're like, well, how would I know that right now? You know what? Let's forget about the long story short. Let's do it. All right, so this is my function, and I want to do the derivative at 0. So that would be the limit of, think about this, f of 0 plus h minus f of 0 all over h as h goes to 0. This would be, if it existed, f prime of 0. This is the definition of the derivative at x equals 0. Now, if this is my function, let's go get them. Now, there's a problem here, right? If x is 0, then 0 plus h, if h is positive, is going to be on this branch, but 0 plus h, if h is negative, is going to be on that branch. So it's kind of like we're split at 0. So to do this limit, I really would want to look at the limit as h goes to 0 strictly from the right. of all of this stuff. And I would want to do the limit as h goes to 0 strictly from the left of all of this stuff. All right, so now take a look at how this is going to play out. F of 0 plus h, that's just f of h, right? So that should be no issue. But if I'm coming in from the right, then which one of these do I plug it into? Well, if h is greater than 0, then the x value coming in from the right is going to be greater than 0, right? So I'd be plugging it into this branch. So this would be the limit as h goes to 0 from the right of, right? Think about it. Absolute value of h would equal h if my values are over here. So we just get h. F of 0 is just 0. The bottom's h. This simplifies to 1. So I just get 1, which makes sense because think about it. The slopes of my tangent lines, all of these, as I'm coming in from the right, all of these slopes of these tangent lines are 1. So you can say they're kind of like remaining steady at 1. As opposed to now, if h goes to 0 from the left, that means h is negative. So 0 plus h, h being negative, that means I'm on this branch. So that means when I go to do f of h, it's going to be negative h. So I'm going to get the limit as h goes to 0 from the left of negative h minus 0 over h, right? And so that would be negative 1, which again makes sense because all of these slopes of these tangent lines are going to be approaching negative 1. So you're like, all right, so then what does that mean about this two-sided limit? Well, a limit's a limit, right? So if the limit from the right and the limit from the left don't agree, that means that this does not exist, which means then that this doesn't exist. So therefore, f prime of 0 does not exist. All right, and you can visually think of it as, well, if it's not a smooth transition, it won't exist. This is more like the calculus mathy way of describing it. The non-mathy way is if you're on a roller coaster and it's not smooth, ain't happening. No good. All right. So pretty cool stuff there. All right, let's take a look at this. I got a couple more questions. Estimate the slope of the curve at the indicated points and then sketch the graph of the derivative. So let's call this thing y equals f of x. Let's give it a name. And let's estimate the slopes at these different values. So like notice I particularly gave you these two on purpose, right? What do you think the slope of that tangent line there would be? Hopefully you're saying 0. What do you think the slope of that tangent line would be? Hopefully you're saying 0. So if I want to graph the derivative now, think about what this graph is telling you. At negative 1, the derivative is evaluated to 0. So when the input's negative 1, the output for the derivative is 0. So that would mean that point negative 1, 0 is on the graph of my derivative. Likewise, when the input is 1, the slope of the tangent line is 0, the value of the derivative is 0. So at 1, 0, there's going to be a 0 there on the graph of my derivative, right? Label these bad boys, y and x, okay? And this will be the graph of the derivative. Now, I haven't gotten it yet. I've only plotted 2 points. And the other one I wanted you to do is here. Now, this isn't 0, guys. If I'm drawing in a tangent line, oh, that was terrible. But if I'm drawing in a tangent line here, right, what would that be? It's not the best looking tangent, but it looks like, I don't know, down 2 over 1-ish if I continued it. So somewhere around negative 2. So I'll plot that. And now the interesting thing is the tangent line 0, then it gets negative, 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 more negative here. Then it gets less and less negative until it gets to 0. So I almost have the derivative looking something like this here. And now what happens after 1? After 1, think about it. That slope is positive. That slope's more positive. That slope's more positive. So after 1, my slopes are getting more and more positive. Likewise, right, to the left of negative 1, this is a little bit negative. This is more negative. I'm sorry, positive. I'm an idiot, right? Because left to right, that's how you read a graph, like you read books, right? So this is not as positive. This is more positive. This is even more positive. As I go that way, it gets more and more positive. So that would be analogous to something like that. So the idea is we're trying to get you to think of, okay, when the inputs are the x values and you know the outputs are the slopes, well, then the slope producing machine, the slope plotter, what's it going to look like? And we're kind of estimating that right now. Now, what's interesting here is this looks like the graph of a degree 3 polynomial. Oop, that's a 3. This looks like the graph of one less than that, a degree 2 polynomial, and that's actually no surprise. That's how it will work with polynomials. The graph of its derivative will always be one less, all right, degree-wise. All right, but again, more to come on that. Let's take a look at this solid little question. So it says the figure to the left shows the graph of a continuous function f, which of the following inequalities must be true. So now think about what they're testing you on here. you see f of b minus f of a over b minus a. So hopefully you know that's the slope of the secant line. So they're testing you on that, right? So do you know that? Then you see f of b, that's just a y value on the graph, right? So this is just a y value, right? Y value at x equals b on f. And then you get f prime of a, which you now know that that is going to be the slope of the tangent line at x equals a. So we have all the meanings here. They're all in here. So let's look at them. So what would f of b minus f of a over b minus a? Well, this is the point b f of b, because it's x equals b. This here would be the point a f of a. So now if I drew in that secant line, all right, I don't know what that would be, but I know it's positive, so I know this is greater than 0, right? Now, what about f of b? Well, that's the y value right here. Well, I know that's actually equal to 0. What about f prime of a? Well, f prime of a is the slope of the tangent line. So if I drew in the tangent line here, I don't know what that is, but I know it's negative, right? Down something over something. So I know that's less than 0. So now if I'm going to arrange these in an inequality, it's going to go f prime of a first, then f of b, then the slope of the secant line. So f prime of a, then f of b, then slope of the secant line. It's going to have to be that choice. So that's a solid question, testing you on just basic things. So don't overthink questions like this. You see these inequalities lined up like this, your mission should be, all right, let me look at each part of the inequality and see if I can give it a value or even just give it a sign in this case, or no sign. All right, 5, last one, right? Good, home free. Here we go. It says the figure above shows the graph of a differentiable function f, which of the following could be the derivative of f prime. So remember, f prime is the slope reducing machine. So I think it's probably best to, well, all right, if this is a graph of f, let me find out when f prime is 0 first. So see where f prime equals 0 first. Well, that's when the slope of the tangent line is horizontal. So it looks like we're going to be 0 here, so whatever that x value is, and it looks like we're going to be 0 here, so whatever that x value is. So when I go to look at my graph of f prime, there should be 2 zeros, right? And slightly to the right and left of the y-axis. So that looks like that's good. This looks like this is decent. This I'm ruling out because it's not 0 at 0, right? Because that's an actual positive slope if I drew that tangent line in. So it can't be that. And then it can't be this either because this would say the derivative is 0 at 0, which it's not. There's a positive slope there. So just by a general understanding, you made this 50-50. So now how do I take it to the next level? Again, look at the slopes. So what would all of these slopes be? So I don't know what they are, but I do know that they're all, hopefully you're saying, positive. So if I drew any slope in between here and here, they're all positive, and they get most positive somewhere in the middle, right? So between my two zeros, look at this. These are all positive values. Most positive, the most positive y value, because remember, the y values on this graph represent the derivative. So the most positive y value is happening a little bit after 0. Well, that's about right? The most positive slope is going to be somewhere over here. All right, so these are all positive and they go back to 0. Now, what about after that, right? So what's going on over here? All of these slopes of these tangent lines are negative, really negative, and then they get less and less negative as they approach that 0 slope. So that's kind of what this is. All of these slopes are negative. Same thing here. 0, then negative, more negative, more negative, more negative, more negative. So 0, negative, negative, more negative, and so on. Now remember, you have to remember that the y values on this graph represent slopes. It's the graph of the derivative. The x values are the same, but the y values in the graph of the derivative represent slopes. So it actually would have to be that guy. It couldn't be that guy. All right, good stuff. Play this video back 5 billion times until it makes sense. See you soon.